Nanoscience and Technology Division and the Center for Nanoscale Materials at Argonne National Lab, and also a professor at the Institute for Molecular Engineering at the University of Chicago. He joined Argonne in 2015 after spending 20 years at IBM Research, where he served as Director of Physical Sciences. At IBM, he pioneered the materials research that led to IBM's high dielectric constant metal gate transistor, one of the most significant developments in silicon microelectronics technology. He was also responsible for initiating or significantly expanding IBM's R&D programs in silicon photonics, quantum computing, sensor-based cyber-physical systems, and photovoltaics. He is a member of the National Academy of Engineering and a fellow of the Materials Research Society, the APS, the recipient of the 2015 prize for industrial applications in physics. He received his PhD in material science in 1991 from the University of Southern California, and a BTech in 1985 from the Indian Institute of Technology at Kharagpur. In fact, that's the same school that I went to, and I just graduated 1 year after he graduated. So welcome. Thank you. Thanks.
Thank you, Amit, for the kind introduction. We did go to the same undergraduate school, and I remember him as an undergrad, very different time, early 80s. What I'll talk to you about today is, nanomaterials for practical applications, and I'll talk about the opportunities that there are in future forms of computing. I'll talk about a couple of areas that I've begun working on after moving to Argonne and the University of Chicago. What I'll try to give you is more of a system level view of things, and then I'll try to pinpoint towards the end where nanomaterials and nanotechnology can have impact. I would prefer to keep this talk informal, so please interrupt me as we go along. Okay? Before I begin my talk, I would like to put a little plug in for the Center for Nanoscale Materials at Argonne that I'm director of. So we are one of 5 national user facilities that's funded by the Department of Energy. We have excellent equipment for nanomaterial synthesis, characterization, etc. All our staff scientists spend 50% of their time on user-based research. Anybody, anywhere can submit a proposal. It's a very short process, couple of pages. If it is accepted, then the work is for free. You don't have to pay anything. As a result, our department has students, postdocs going through it at all times. I would very much encourage any of you interested in working with us. We are looking for collaborators. Please send me an email. I'll connect you to the right people. But the areas of expertise that we have a hard X-ray nanoprobe that's attached to the synchrotron. You can do 3-dimensional imaging using tachography with 20-30 nanometer resolution. It's unprecedented. I think it's one of only 2 pieces of equipment anywhere in the world. We have a fully functional clean room nanofab capability, specializes in MEMS, in photonic structures, plasmonics, extensive characterization synthesis equipment, extensive scanning tunneling microscope equipment, coupled with things like optical beams, magnetic fields, things like that. So, please send me an email or chat with me today, and I'll be happy to connect you to the relevant people. And we also have a very strong theory group whose current focus is on trying to merge first principles physics along with machine learning type approaches. So this is how I like to begin my talk. In the late or the mid-1600s, Robert Boyle, whom you know is the father of modern chemistry, came up with a list of 24 things that he wanted to see happen that hadn't been achieved at that time. And if you go through the list, you will find that a bunch of them are related to material science. Many of these things we've achieved, and many we still haven't. For instance, if you look at item 2, coloring of hair. We can certainly do that. It's too late for me right now. The art of flying we've achieved. But certain things like number 11, the making of glass malleable, we have not achieved. Polymers are not a solution, I think. You look at the last one, the perpetual light. I think with solid state lighting, I believe we have achieved that today with gallium nitride. But if you go through this list, there is one item that's missing in this list, I feel. What do you think that is? Any guesses? Which he should have caught. Anybody? Vishaki, you're an assistant professor. You have a guess? Okay. All right. So, computing, I think, right? He doesn't talk about computing. That is surprising because Boyle said that he was a good mathematician, and there were people trying to make mechanical computing machines at that time. People were trying to measure, try to calculate star charts. The logarithmic tables have come along. So it was surprising that Boyle missed computing over here, and that is the subject of my talk. And if I go to the next chart, this is from Ray Kurzweil's book. And the reason I show this plot is that it shows that the price of computing has gone down by a factor of by about 15 orders of magnitude in the past 100 years. And about 7 or 8 orders have been gained in the past 40 years because of silicon microelectronics. And this is what has fueled this enormous information boom that we've had. All of you are probably familiar with Moore's law, and this is what has driven us so far with all the benefits. But this is also coming to an end. People anticipate there's a few things that are happening. The performance scaling of transistors have come to an end. I'll talk about that in a moment. The cost to build a transistor is reaching a constant value. This is a strong business reason why this technology is saturating. In the past, transistors would become cheaper with every succeeding generation. Today, the price of a transistor remains the same. As it increases density, the cost of the chip increases. This becomes a problem. Okay. And then there are changing workloads because of big data and analytics and this entire goal of trying to find patterns in large masses of data, etc. Okay? So because of a bunch of these different things, computing is sort of changing. So far, the benefits in computing have happened because of microelectronics. The basic architecture of the computer, the von Neumannian architecture, has not changed since the 1940s or so. So there's a lot of interest in trying to come up with new types of architectures for new types of workloads. But let's spend just a minute or so in looking at how silicon microelectronics has evolved over the years. In the early 1990s, what we used to call mainframe computers in those days were all driven by bipolar silicon technology. And then we came up against what's called the power wall, which meant that if you continued to improve the performance of the computers, the heat dissipated was becoming enormous. That was the time the technology switched over from bipolar to CMOS. So IBM led that effort. They saw the power of Moore's law, and they recognized that in the early 1990s, if they switched to CMOS, things would probably still not be as efficient as bipolar, but in a couple of generations it would catch up and then supersede it. And that's exactly what happened. And so from the early 1990s to about the mid-2000s were what's called the golden age of Moore's law scaling. So all of you probably know the way you make a chip is by patterning it and using masks and so on. And what they essentially did is that they would take the the mask, they would shrink it by a factor of 0.7 and increase the number of devices in the chip every 2 years, and that's what gave you density scaling. And due to some interesting consequences of device physics, every time you made the device smaller, the performance increased, the voltage required reduced, the power per circuit reduced, and so you got performance scaling. So you got density scaling, you got performance scaling, and that's what drove things till the 90 nanometer node, till about the mid-2000s. And at that point, new materials started coming in. We replaced the silicon oxide in the MOSFET with a high-K hafnium oxide-based material. We replaced polysilicon with a metal gate. We started putting germanium in there. And those things then drove Moore's law till we came to the 22 nanometer node. And then we went away from the planar geometry and went into what are called FinFETs to get basically more gate capacitance and reduce short channel effects. And right now we're at a point, we're at the 14 nanometer node, and we're at a point where people think that maybe in another 5 to 7 years, we will run out of steam as far as the scaling of the silicon transistor is concerned. Okay. Going forward, there will be other things that will happen. Beyond the silicon transistor, there's a lot of interest in using carbon nanotube transistors to replace silicon. There's a lot of work in non-volatile solid-state memory. Think of future machines where the processor is going to be surrounded by bulbs of memory, non-volatile memory, instead of volatile DRAM. Silicon photonics is going to come in a strong way. There'll be on-chip power conversion. So all these technologies will combine, these 3D technologies, these will all combine and push things forward. Though there is no clear anticipation of a Moore's law-like thing where these sort of benefits will continue pushing the technology forward for a long period of time. So that is unclear. So now coming back to the question of architecture, as I mentioned to you, there's a lot of interest today in new forms of architecture, and I like to visualize that interest in the form of a sort of three-branch tree. Okay? So the middle branch here is what I just spoke about, conventional scaling of silicon technology, 3D structures, silicon photonics, non-volatile memory, etc. And over here, I think eventually this gets into sensor networks, which will be a big part of my talk today. Sensors, computing at sensing nodes. And the way I view this thing are sort of distributed sensor networks forming a new form of computing. I think that's one direction where conventional computing is going. Okay? Then there's the other branch, which is quantum computing, and I will not talk about that. Companies like Google, IBM, they are the leaders in that field. This is a field where the current status is at the level of few numbers of devices that are being combined into circuits and so on and so forth. And then there's a third branch which emerges out of neural networks. As most of you know, we use neural networks today at software level in our daily lives when we open Amazon or Google or any of those services. So the next step has been to say, well, can these neural networks be sped up in terms of energy efficiency by using dedicated circuits? And this work has started out, and these dedicated circuits are still based upon silicon CMOS. And so you must have heard of IBM's 2-node chip. That's an example. NVIDIA has come out with an example recently. So there is movement in this direction. However, there's an argument that silicon CMOS may be convenient for making neural network chips, but it may not be the most effective approach in the long term in terms of energy efficiency and cost. And so there's a lot of interest in looking at new materials for neuromorphic computing where the function of a neural network algorithm or parts of the function can be combined in a new type of material where you use defect chemistry or stoichiometry in the material or the structure to achieve those functions. And I'll get to that in a moment. So in my talk, I'll talk about these two yellow areas, a little bit about the work we've started in neuromorphic materials and devices, then I'll switch gears and I'll talk about 3 projects that we're doing in the area of cyber-physical systems. It might seem disparate to you in a way, but in my mind, it all sort of heads long-term towards the same objective, which is where, where's computing headed beyond the sort of conventional type of computing that we do today. So those are the 2 things I'll talk about. So let me start with neuromorphic computing. So let's table at the top compares biological information processing systems and our world of silicon microelectronics. And there are a few key differences. There are some obvious ones where silicon works at gigahertz speeds, biological systems work at kilohertz speeds. Voltage differences, we use about 1 volt, biological systems about 100 millivolt. And a big difference that people usually don't talk much about is the fan out. And fan out is, if you have 1 wire coming in, how many wires can it split into? In silicon CMOS, typically the maximum fan out you will have is about 4. And that is because you are limited by Kirchhoff's law. Right? You have a remote power supply, you have joule heating along a wire. If you want a wire to split into 100 little wires, you better have a real thick wire coming in. So you're limited. You look at biological systems, that's the beauty of it. The power is not coming from a remote source, but it's coming from the surrounding path. Right? There's a voltage spike that forms at the membrane of an axon due to differential migration of ions, creates an Nernst potential that then skims the surface. So you can have fan-outs of 100,000 because you're not, you're delivering the power where it is needed. This is a big difference. There has been almost no work on looking at new forms of delivering power in electronic systems. And I think this is an area where a lot could be done. Okay? And then, of course, there is the matter of energy efficiency. You may be familiar with the Jeopardy game that was played where IBM's Watson machine played against the top Jeopardy champions. This was perhaps 5 years ago or 6 years ago. And the interesting thing to compare there is that the human players, their brains consume roughly about 20-25 watts of energy. But the machine that beat them consumes about 80,000 watts of energy. So that shows you the difference in power efficiency. That's the gap right now. Our architectures of computing and biological systems. So when you look at new materials that we're trying to use to build devices such as that can mimic the performance of neurons or synapses from a computational point of view, there's a lot of materials in the area of oxides, chalcogenides, oxychalcogenides that can be effectively used. So if you look at a neural network today, and the way I'm looking at this is from the computational point of view, not the biological point of view. So saying that, look, here's a neural network algorithm that we need to solve effectively. So in this neural network, we define things like neurons and synapses that approximate the function of a biological neuron or synapse. So can we make, it's a simple question, can we make these neurons and synapses with new materials and devices in an effective way? Today, for instance, in silicon technology, if I have to make a synapse, we think of it as a weighted resistor where you can write a certain resistance term in. Today, a synapse in silicon technology is built by using SRAM arrays. That's expensive, that's large. Today, a neuron in silicon CMOS, so think of a neuron as something that is collecting, integrating charge coming into it. It's a certain threshold, it fires, and gives out an output waveform. And then after the waveform is delivered, there is a period of time when it doesn't integrate charge anymore. So in order to achieve that, you need something like 8 to 10 transistors. Again, that's large, that's expensive. So simple question, can we have materials that can replace and mimic this function, right? So for synapses, people work on things like things that have come out of non-volatile memory, things like phase change materials, resistive RAM, conductive bridge RAM materials, where you apply a bias across a dielectric oxide, and you have things like copper ions or oxygen vacancies, you form filamentary breakdowns that you can write and then erase. And this is how you write a resistive state, and there's a lot of work going on in this area. We are working on this, but in the interest of time, I will simply talk to you about some of the recent work we've done on mimicking an artificial neuron. So the neuron, as you recall, you have a node that's collecting charge and then firing once it hits a certain threshold. So for that, we use metal to insulator transition material, and a prototypical one is vanadium dioxide. Right? So what happens with vanadium dioxide is that if you heat it, if it hits beyond a certain temperature, around 70 degrees or so, it goes from being an insulator to a conductor. Okay? So we use this property effectively in building a neuron driven by positive feedback, as a biological neuron is. So we have this circuit, right? We have a capacitor, and connected to it is a series resistance and an insulator to metal transition element. So if you start loading this capacitor through either a voltage or a current, which in the biological world they call a voltage or a current plan, then the voltage across this capacitor keeps increasing. There's certain leakage through the IMT, insulator to metal transition element. So once this leakage crosses a certain threshold, it starts heating up, and then it goes from being an insulator to a conductor. When that happens, there's a spike across as the current flows through it. And once this spike is completed, this guy is still hot, it's still shorted, so the capacitor does not integrate charge anymore. And then once it drops below the temperature of its transition, then it starts integrating current again. Okay? So using this, my postdoc, Jerome Lin, he demonstrated an artificial neuron that works at about 0.5 volts. That's lower than what silicon can do. He's replacing with two device elements, a capacitor and the vanadium dioxide element. He's replacing 8 to 10 transistor device. That's sort of the goal over here. Right? So this is what I mean by saying trying to take the functionality of these biological elements, such as neurons and synapses, and somehow building it into the functional design of the material itself. Okay? So our long-term goal is to build a neural network engine using these types of native neurons and synapses. This is work just started, but hopefully in the next few years, we will be able to build demonstrators, simple demonstrators of things such as handwriting recognition or image recognition. This is sort of the goal. Okay? So let me switch to the next topic. I'm going to switch gears here and talk to you a bit about sensing networks that we're working on. I'll talk to you about the challenges here, and then towards the end, I'll give you some specific examples where nanomaterials and nanotechnology can make a real impact. Okay? So this is work I started in IBM about 10 or 12 years ago. I was a manager of the group that started this work. My colleague there, Henry Kaman, was actually the technical pioneer here. But think of a sensor network as a collection of sensors. They send their data through a wireless technology link to a curation platform on the cloud. And on that curation platform, you're constantly aggregating and accumulating data, which you can then take and analyze through physics models or analytics models, and then push recommendations, etc., to smartphones. Right? This, in my mind, is a cyber-physical network, and you can think of being able to screw the sensors in and out like light bulbs, and everything else kind of remains the same, right? Then it's a nice scalable system. This is what's called an Internet of Things or cyber-physical system. Today, in big data, most of the data comes from computer transactional data, marketing data, sales data, things like that. Going forward into the future, there's going to be an emergence of physical data coming from physical sensors. And this is where the importance of these cyber-physical networks will become. Okay? What I'm here to argue to you today is that this whole field, okay, is gated by the availability of cheap, power-efficient, and accurate sensors. This is what gates us today. Okay? And this is where I think the calling card of nanotechnology could be, developing new sensors. Okay? I will give you 3 examples today in areas that we are interested in. 3 very quick examples. One in agriculture. This has been work that I was lucky to be involved in somewhat while I was at IBM, along with my colleague Henry Kaman. This is a joint project that IBM did with Gallo Wineries in doing a pilot for wine growing. The second example I will give you is a buried sensor network that we have just established at the University of Chicago. And the third example is a project that we are about to begin. It's a Gates Foundation funded project on doing developing a sensor network for a river in India to measure and assess water quality. Okay? So let me go through these, and in describing the project to you, I'll talk to you about some of the challenges for sensors, but what I'd also like to sort of emphasize to you is that in this business, we have to take a system-level view of things, that in the end, people are interested in a sensor network. They just set up a network, and in the end, there's some conclusions that are coming out of it. People are not interested so much in all of the individual little pieces or the material science that goes on in building a sensor. So this is where I think our research is headed, and we really have to begin to take a sort of system-level view of things, at least as far as engineering research is concerned. So let me start with the Gallo project. And as I said, this was a project between IBM. I was there at IBM at that time, and Gallo Wineries. Nick Supratik Guha, my colleague there, who the visionary guy, is the vice president of research at Gallo, who also championed this. So this was a 10-acre plot in Lodi, California, growing wine grapes, and the way you irrigate vineyards is you have what's called drip irrigation. There are plastic tubes with holes in them, and then you turn the water on and it irrigates the soil. Okay? So because you have drip irrigation, you can pixelize the irrigation, which is what the IBM team did by putting valves and things like that, so that you can deliver water in specific amounts to, say, 15 by 15 meter square plots. Okay? So that was the hardware change that was done. And then for the first studies, in this 2-year pilot, what we used as the major input was satellite imagery data. Okay? So how many of you are familiar with Landsat satellite data over here? Okay. Great. So you can get for free Landsat data twice a month from any region in the Earth, and you get it in 11 or 10 different wavelength bands, from the visible all the way to the thermal infrared bands, which are 10, 11 microns. So you can think of it as a way of doing spectroscopy. So in this case, we used the red and the green bands using standard approaches to calculate what's called the NDVI. Think of it as a way of getting the greening, the chlorophyll map of the canopy. Okay? So it gives you sort of, how green is the canopy with about 15 by 15 meter resolution, approximately. So we take the Landsat images and we calculate the greening as a function of X and Y in this plot. Then we got the weather data, wind speed data, moisture data, etc. Then we use standard agricultural models to calculate what's called evapotranspiration, which means you calculate how much water is evaporating from the vines. And then based upon that number, we irrigated to those pixels, whatever was needed. So the water delivered was a precisely calculated delivery from the satellite data and the wind speed data and all that. And it was spatially based, as opposed to the past where this was done just sort of, through your experience. I will not go into the details of all of this, but then this was a 2-year experiment, and
before you move on, just a quick question, just about, did you use digital elevation maps?
Say that again?
Did you use digital elevation maps for that region?
No, not over here.
So is it a flat region, so you don't care?
This was flat.
This is absolutely flat.
This is a vineyard, right? So, this is a picture, for instance, of the drip irrigation lines, that we pixelized to deliver the water. These are just some of the equations for calculating NDVI, but let me get to the key results. So there are 2 things, the Gallo guys measured based on this analysis. One is the yield, and the second is the water efficiency. Water efficiency is that how much water do you use for, say, a kilogram of grapes produced. And in both cases, we saw 10 to 20% improvement in water efficiency and yield increase. And I am no agronomist, but my understanding from talking to the Gallo guys is this is a significant difference. And keep in mind that all of this was done just purely based on satellite data, right? And even at that, there was a major benefit. So now think if we can have in-ground sensors, right, in the ground. Here's a list on the left of all the kinds of things that can be measured, and I've talked to a lot of agriculture folks. These are the kinds of things that we measure. It's a big list. But forget about this big list. There are just 3 things that if we could measure, is my understanding from talking to agricultural scientists, would make a huge difference in agriculture. One is if you could measure the amount of dissolved nitrates in the soil. Okay? That can allow you to control the fertilizer. So that's big. There is no good, cheap way of doing that today. The second is moisture content in the soil, but averaged over meters. Okay? So soil varies on the scale of 10, 20 meters. If you put a point probe, you might hit a bucket of water, you might hit a hole, you might hit a rock, you don't get consistent data. You want to average the data, so you want to measure that. Third is microprecipitation, the amount of rainfall that's happening over a scale of 10, 20 meters. Again, there's nothing good for these types of measurements. If we could just have cheap, effective sensors for leaves and be able to plug it into a cyber-physical system for agriculture, there would be enormous benefits. I'll talk to you about some of the price challenges here in a moment, but let me go to the second part. Second example I'm going to give you is now driven by this goal of, okay, can we have in-ground sensors, can we have a cyber-physical system measuring the ground for either agriculture or environmental soil management. There's tremendous interest in looking at the long-term biochemical evolution of the soil, the carbon cycling, and so on and so forth, as well as agriculture. So what we decided to set up on campus at the University of Chicago is a buried sensor network, which is now operational. This was done by one postdoc essentially, and one really bright undergraduate student. So this is one of the benefits I'm seeing of coming to a university, is just the excitement and brightness that these undergrads bring. So our goal here is twofold. One is try to see what this sort of data can do. Can we build a scalable system so that if you can put X sensors today, X plus 1 becomes easier? I have been trying to do this for quite a few years, and in the past it had been frustrating, but today wireless technologies, things like that are coming to the point where someone who's interested in building a system can walk in and start building things. It's not quite there yet, but it will come. Okay? Price is the issue here today, and I'll come to that later. The goal was to have drop and forget sensors fully buried. Even the antenna is buried inside the ground. I'll show you examples. And we want this to be sort of a neutral platform at a university where we can do things like sensor development, benchmark different wireless technologies against each other, try to do physical analytics or analytics on the data, and so on. So in terms of wireless system, there are a few options available today. We used one called, provided by the company Sigfox. They were very kind to give us a system, base station and antenna. It's a small setup. The key thing about the Sigfox system is that it is extremely low power. It works at 900 megahertz, ultra narrow band. It's 12 bytes per packet, so you can't obviously send images, but for soil data, it's perfectly fine. So battery lives are very long. So this is something they gave to us. We mounted the antenna on a building on campus. We can pick things up within a couple of miles, even with buried sensors. Okay? And the goal is these types of IoT systems, be it Sigfox or be it LoRa or other alternatives, I feel will soon permeate at least the major cities, and then it will start permeating elsewhere. And I see a future where you can hook sensors onto these networks, and it will completely change the way we do a lot of businesses and the way we do a lot of science. Now, sensors need to connect to something that then beams the signal up, and those things are together called modes. So a sensor comes in, there's a little microcontroller unit, a little power management unit, batteries, there's radio, there's an antenna. We spent a lot of time packaging this, making sure that the power consumption was very low. Right now, these boxes as built for us, and we use standard chips, standard TI chips, etc. But these boxes are roughly 4 inches on the side. That's our zeroth order design. This can probably be cigarette packet sized eventually, if not smaller. We put them in before the winter. We wanted it to survive the winter. It did. Battery lives are 5 years plus. That's what we anticipated, and our projections are in total agreement with that. This was behind the idea of drop it in, dig a hole, drop it in, forget about it. Seems like that's working. These are just some pictures of the TI chips, etc. we used. And then this is a campus map showing the location of the sensors. Let me just open these up. So we would dig a hole, put the thing in with the antenna, everything, and then cover it up. And once you cover it up, you know, the thing is 6 to 18 inches below the top of the surface. So we wanted to do that so that if you till the soil, things like that, you're not interfering. So we put a little flag there as a fiduciary mark, so we need to go back and retrieve, we can do that. So that's how it looks. And then, you know, right now we have about, I believe, 25 or 28 sensors, and then once winter is finished, we're going to be putting a whole bunch of more sensors in there. It's all working. If you go to the website, in here, if you go to the website thorough.uchicago.edu, you'll be able to see it live, all the sensor data being collected. I think we are in a position where we started putting heat maps in as well. We've done studies on the wireless piece. Initially, nobody believed us that we could get wireless transmission of the signal, but we do. When we calculate these things, we figured we would. Red is the calculation, black is the actual signal received. Basically, the signal refracts out of the soil. You know, it depends on various things. It depends on the content of the soil, you know, whether it's clayish or sandy or rocky. But for practical purposes, 1.5, 2 miles, we get enough signal for the kind of work that we are trying to do. So, okay, give me a second. Okay, so over time we are accumulating dense data of heat maps of various parameters. These are just some examples for the first time we are doing this. Right? But think about it. Over time, if you are measuring a whole bunch of parameters about the soil, very dense spatial resolutions, day after day for years, will give you unprecedented scientific advantage to study various things about the soil. And this is why we named the website Thoreau. So Thoreau was the American naturalist, as you might know, who lived near Walden Pond in Massachusetts in the 1800s. And he was one of the early naturalists, along with Alexander von Humboldt, who actually measured stuff, right, in microclimates. Thoreau would note when the frost happened, the colors of the flowers changed, what happened to the pines, when, and he kept detailed notes of this. And this changed, deeply influenced environmental science. And today, with these sort of sensing technologies, measuring our environment at high resolution over time gives us enormous advantage in being able to do unprecedented things. This is what I believe, right? This is what I'm excited about. You can already start seeing correlations. For instance, this is an example where this is one of the sports fields. We have a moisture sensor or a volumetric water content sensor. So every time the sprinkler comes on, this thing comes on and it goes down. Right? It depends on the type of soil. If this were sandy soil, it would come up, then it would be flat for a while, and it would suddenly go. Any such approach, even if it has science objectives, it helps to have a few quick business implications. So something like this can be used, for instance, with sprinkler systems in an automated way. Once you have these types of low-power IoT wireless systems available, and we're looking into that with the physical plant people at the University of Chicago. You see wireless signals change as a function of rain. You can see correlations expectedly between the soil conductivity, volume water content. Start doing statistical analysis. You see that the temperature of the soil lags the air temperature by a day. So again, these are just simple examples of things, correlations that we are already beginning to pick up. So now it takes me to the third example. This is a project that has just begun, so we don't have any real data yet, but this is a project of measuring water pollution in a river in India. So this is an example of the Ganga River. It's 1,500 miles long. It's one of the most polluted rivers around. It feeds about 30 or 40% of India's people live on its plains. It's 1,500 miles long, but it only has about 57 water quality monitoring stations. One of the big pollutants here is E. coli. The E. coli numbers vary in the Ganga anywhere from, say, 100 to about a million colony-forming units per 100 milliliters of water. If that limit were more than 300-400 in the US, you wouldn't be able to swim in that water. Okay, so just as a comparison. So there's a lot of interest in India in measuring these, and not just measuring it, but trying to predict the flow of pollution or trying to pinpoint sources of pollution. So a lot of the pollution comes from what are called tributaries or nalas that feed into the river, and there are sewage treatment plants, right? A lot of them work well, a lot of them don't work well. So in the long run, I think this, if you can monitor and map using a sensor network, water quality, you could predict or you could pinpoint who's following regulations, who's dumping stuff, that sort of thing, through inverse problems. But the first issue here is, can we map and sense and do this thing properly? And so we have a pilot project that has just begun for the Godavari River. This is funded by the Gates Foundation. We're setting up shop in a place called Rajamundry. And I'm actually going there next month, and we'll be starting the first experiments. So there are a few things about doing sensor networks in India, right? So you can look at either a fixed sensor network, like I showed you on the U Chicago campus, or you can say, I'm going to spend a little more money and buy a mobile sensor network and move the mobile sensor network around, and as long as it has GPS, I can do the same map, right? So we're doing a mobile sensor approach here, partly because we can rent a boat. Labor is relatively cheap. We can rent a boat and have the sensor platform go with the boat. The key thing here is that we want the measurement to be automated. We don't want to rely on an operator to do the measurement, so it should automatically take the measurement, take the location, and then either send it to the cloud at that point or send it to the cloud the next day or at night. Those are details that can be worked out. The other issue is that with fixed sensors, you might be worried about the sensors getting stolen. Okay? So you always have to kind of think about a whole bunch of different things when you're doing sensor networks. These are really field experiments. There's a big social part in it, a social human engagement part in this whole thing. So our approach here is to go with a mobile sensor platform. Initially, we're going with a commercial platform that measures standard parameters like conductivity, turbidity, which means the amount of dirt in the water, dissolved oxygen, and so on and so forth. If you want to measure things like E. coli and biochemical oxygen demand, which is a measure of organic content in the water, these are longer-term tests. The ones that are truly qualified tests take 2 to 5 days to do. Or the equipment is tremendously expensive, okay? So this is a big problem, and there's no good solution. So we are working in the lab on trying to figure out ways of detecting E. coli in a quicker way, okay? In and out. So working on trying to combine, say, Raman spectroscopy along with silicon photonics. You use the Purcell factor to enhance signals. That will take time. Another approach is to try to measure a bunch of other things and use that as a proxy to see if there's any correlation with E. coli or biochemical oxygen demand. But again, these are two things. I gave you a few examples in agriculture, the key areas for sensors, right? Dissolved nitrogen, moisture, precipitation. In water, it would be, you can figure out a nice way to functionalize, maybe using fluorophores, E. coli, okay, at very low densities of 500 to 1,000 for 100 milliliter of water, and make those devices, it would be fantastic. I mean, you would be, very famous. Same thing with biochemical oxygen demand. The way it's measured today is you measure dissolved oxygen today, and then 5 days later you measure it again, you take the difference, and that gives you the amount of organic species because it eats up the dissolved oxygen. If you can accelerate that process using some photocatalytic materials or something like that, I don't know, okay? But if you can accelerate it in a reliable fashion, again, it would be tremendous benefit. So I personally think that we've spent a lot of time and effort looking at nanomaterials, nanotechnology for computing devices, and that's good. We've hardly spent that on effort on sensors. So sensing technologies, I think, have big room for improvement, and that time is now. So if you look at a sensor platform, right, it needs some silicon CMOS, that's cheap and available. It needs optoelectronics because then you can have light sources, spectrometers, things like that. That's also come, okay? You can buy lasers, detectors for a buck or so, right? But that's system on a chip improvements that happen. So I think there's a big room now in just developing ways of sensing some of these critical elements in a cheap way. Okay? That's the challenge. Let me come back to the matter of agriculture and give you some price numbers. Wine grapes are expensive, about $1,000 per acre. Over there, we calculated that if you need a return on investment of about a couple of years, then your sensing unit needs to be less than $100, right? For this to make sense, because you need to place these every 20 meters or so, because soil varies on that landscape. Now, today you can buy these types of wireless sensing stations with some sensors. It will cost you between $800 to $2,500. So it's way too expensive. And this is why this stuff isn't there in a ubiquitous manner. You can place one maybe every acre or so, but then it's not that useful. Okay? And that's for wine grapes. Now, look at these other crops. Sugarcane, $1,500. Winter wheat, less than $100. So cost is a big, big factor in all of these sensor networks. Okay? Cost, efficiency, and accuracy. These are the three big things. But going forward, I visualize this whole business in the context of a geopixel. So you can think of a little patch of land as a geopixel, and against it are stacked vertical layers of information. You can get it from satellite and government public data. That is already happening. There are many, many new satellites coming into space. There's a European satellite that went into operation last year. If you look at the large companies, they are mirroring, I believe, these government sites and accumulating all this data. And you can have data coming in from in-ground sensors. And then you can use these layers of data to create new layers of data, like I showed you for evapotranspiration, where you take data on greening of the canopy, weather, etc., calculate how much water is evaporating off of a plant, and you could do that. A whole bunch of things, and then feed it into science, environmental management, and agriculture. So this is sort of the way I see, these cyber-physical systems evolving in the context of maintaining, this sort of geopixel information. And I will conclude with this last slide. This is the Boquilla vine. This is a very interesting vine. It grows in Chile. So the key thing about this vine is that when it grows on a tree, the leaves of this vine end up mimicking the shape of the leaves of the tree on which it's grown. Okay? It's amazing. 3 examples. And this vine does not see in the way we think we see, right? But this, to me, is the first forms of intelligence in a distributed sensing network, right? This is intelligence to me. And this is, I think, the future of computing in the sense of a distributed system. And this is where I think all these sensing networks, cyber-physical systems, will head to. So with this, I will conclude my talk and take any questions. Thank you.
Thank you for a very interesting talk. Time for questions.
I really like your message about, you need this entire system, and the cyber-physical system in particular. But some of the other researchers are talking about it, you showed also in your slides earlier, we have this sort of, close the loop where from the sensing to data analytics, and then usually when connected to the physical world, you also have the actuator that controls the system. Like in your example of irrigation, it would be nice to have the AI, the data analytics system to drive the actual control, the valves and all of that. Can you comment on that?
Yeah, and that is of course a very good point, right? So yes, I Ideally, that has to happen. In many cases, I see that as two parts because, so your system gives you recommendations. And many times the actuation part, the customer wants to take care of themselves, right? So if I go to a farmer, right, I can say, look, this is the recommendation. The farmer might say, I might make my own, give me the recommendation, and then I might make my own adjustment in the actuation, or I might have my own trade secrets in how I end up closing the loop. So that's why I've kind of kept the two separate, but it's a very good point, and certainly that's the entire system that makes sense.
Any questions? Taro?
I want to preface this statement saying I really like the neural network approach where you're trying to reduce performance such as I see a lot of applications. Philosophically, these things are good at doing interpolation and bad at doing extrapolation. And if I use these in an automated manner, believing it's doing well, I have a black swan, an outlier event, and this thing can go very high.
It's fair enough. I'm not a neural network expert, right? So the way I'm looking at it is a very simple, practical way, saying, look, there are all these workloads that are coming that are neural network based that people are using, handwriting recognition, image recognition. I'm a chip guy. Somebody wants to make chips, maybe there's an opportunity here. And I believe there's an opportunity of doing this in a very energy efficient way, maybe improving it by a factor of 100. Now maybe these algorithms are not the best, which is what you're saying, they won't catch outliers. That may well be the case, right? It's not something that I'm an expert in. Right? I'm kind of seeing them as customers, I figure maybe they know what they're doing, they want a chip, I'm trying to give them a chip. So, but good point.
Chris?
So we're at the point where we have two kind of in numbers. We have cheap and crappy, and we have expensive and good when it comes to these sensors. How do we calculate where the sweet spot is? How do we know we're not already there and there's some combination between cheap and crappy and good and expensive that tomorrow we can't go to a field and say we can calculate soil moisture within an accuracy of 10% and hit these kind of markers that work for wheat?
Right. So you said, good and expensive, cheap and crappy, and then there's a third part to it, which is the specific application.
Hybridization of those two. I mean, you think about what someone can do with an Arduino chip
Right.
and a 99-cent soil moisture probe. Yet, how do we calculate that sweet spot? And how do we know we're not already there?
We are not there in agriculture because, and I spent quite a bit of time, finding out about this. If we were there in agriculture, you'd be seeing this being used. People are aware of this kind of thing happening. And if, at the end of the day, if the agriculturist does his return on investment and doesn't feel it's going to work for him, he's not going to take it. So we're not there in agriculture. That part I'm pretty sure of. How do we estimate the sweet spot? That's a good question. We can make approximates to it in the way we've been doing, saying, okay, this is the cost of, land, this is the cost of the crop, I want to do a 3-year, this is the yield benefit I will get. So you can do these calculations. How accurate they are, I don't know. They certainly have error bars.
So what is the most expensive part of the sensors you're using?
Today?
Right.
Well, today the whole thing is, like if I were to buy, let me give you an example. If I want to buy a decent, conductivity sensor, that's going to be reliable, that's going to last. If I go commercially, I'm going to spend like a couple of $100. Okay? And the point I'm trying to make is many of these sensors don't exist today. Right? E. coli sensor doesn't exist, so it doesn't matter if it's cheap or expensive. I mean, there's biochemical oxygen. There's stuff that you can buy it, maybe it'll cost you $5,000, but those tests are not the most accurate, and they are not accepted by EPA type agencies or whatever the health agencies are concerned. So we're still looking for that sweet spot. I don't have a clear answer for your question. It's a good one.
So for large-scale agriculture such as wheat or corn, which makes more sense, use the satellite data or drone data versus
I think for that, probably in-ground sensors is going to be tough for something like winter wheat. There's other things that could be beneficial there, where you could measure properties of soil and use that in the engineering of the seeds. Right? That's a bigger scale issue. So for instance, in the Midwest, there are, I think, 100 varieties of winter wheat. So what do you use with respect to what soil condition? Maybe you don't need to do that on a day-to-day basis, but maybe you do that every few years. So those are the kinds of sensing things that we could do with use.
Other questions? Go ahead.
So I guess how do you I guess decide the spatial extent that one sensor would be measuring in terms of depth or in terms of the
Right. So the question was, how do you decide the spatial extent in terms of at which you measure? So again, I am not an agronomist, so I've asked this question to agricultural professors, and the answer that I get for soil in X and Y is 10 to 20 meters. Okay? That's the resolution they ultimately want. If you talk to the real visionary guys, they want it at a single plant level. Okay? They want to engineer what you're delivering to a single plant. I think that's very far out. The pragmatic guys want it 10 to 20 meters. In terms of depth, I've gotten answers that are varied. Typically, it's between 12 to 18 inches below the surface. Some want the surface profile. Some want the water uptake in the plant, not so much the soil moisture content. So they want what's the water potential in the plant. And in that relation, many want to know root mass. So there is no good way of figuring out how much volume or surface area of roots you have for a plant or a tree. And that's something that's an unknown. They do all kinds of approximations, I believe, in figuring that. So that's another thing when I ask them about water, because they say, well, can you also give the root mass? So that's another sensing opportunity.
Go ahead.
Thank you very much for your presentation, very interesting. I'm from geography department, so we usually use like satellite data, remote sense data. So, and I think most of them are, and more census data are like available, especially free data, like NASA and other kind of data. So, do you have any opinion like about the advantage of this kind of local sensor or local sensoring compared with remote sense data?
So there's pros and cons. I mean, satellite data is cheaper, but the resolution is poor. The visible wavelengths maybe 15 meters. In the infrared, it is much larger, right? So resolution is a big issue. In satellite data, you're usually doing all kinds of models, approximations to calculate it. So for surface moisture, it becomes hard. I think it's almost impossible to get dissolved nitrates. Right? So there are limitations, but the advantage is it's cheap and you can get, big picture. Even things like if you can predict the amount of crops that will be produced, right? That has big implications in the stock market and so on. If you can predict before the food agencies come out with their predictions of how much winter wheat, how much soy is being produced. Those things are, I'm sure there are people doing that too, but that's another area where satellite can be used. I think right now the satellite data is all available, but it's kind of clumsy in the sense that if you're not an expert in this area, you're lost. They're all on different projections. You want it in a very simple way. You want to click and you want to get what is there. But I think companies are trying to kind of regularize that and put it in one sort of simple projection that a common person who's not a GIS expert can also benefit from.
Yeah, I think maybe Google they are also doing this kind of.
Yeah, all of them are mirroring those sites and collecting the data. If you make a little calculation of the amount of data, it's huge.
Thank you very much.
One more question?
Again, going back to that system view, I'm sure, in order for the system to work, you need the wireless link to work, you need the data analytics people. Are you guys working with folks working on, for example, wireless communication?
Oh, yeah.
And data analytics?
Yeah, so Monisha Ghosh, whose name was there at the bottom of this, she's the wireless expert. So she's a wireless signal processing person. So the wireless piece was all done by her. There are different options in wireless, and it's the same way with analytics. We're starting to work with people on the analytics side. We don't have enough data yet to seriously interest a powerful analytics guy, but we're getting to that. From my point of view, again, going back to the system level view, I want a wireless system that I can easily use. 4 years back, if I did this, they'd send me a big spreadsheet, Bluetooth, this, do that. It's just confusing, right? I'm not an expert, I'm not interested in that stuff. Give me something simple. This is coming though, with Sigfox's system. I think it's very straightforward to use. Still requires a little bit of programming to the hardware. LoRa is another standard that is emerging. So.
Any other questions? One more over there.
Is IBM or any other company working on on-demand power delivery within the chip to make it more power efficient?
I don't know about IBM anymore, but there's a lot of work going on in power efficiency in chips, particularly IoT type of chips. If you want to find out more about it, there's a professor called David Blau at the University of Michigan. I think he's one of the leaders in that area. That's his name. But there's a lot of work going on on low power IoT chips.
Talking about mimicking the biological system that
Oh,
you
you-
talked about earlier.
I'm sorry, you're talking about delivering power.
Yeah, delivering power.
As far as I know, there's nobody who's working in that sort of area. I think that's the right area to work in, alternate forms of power delivery. I am personally interested in sort of having delivery of power through some liquid bath that can also cool the system at the same time while delivering power. As far as I know, there's no
So Supratik, it's a small token of appreciation for doing the Renew Innovation Lecture. This is for you.
Thank you very much.